So, good morning. Yesterday, we started to talk about materials which are polarizable, or what the effect of polarizability um, does to the electric field, or we started on that. So, we here introduced the two types of the three types of materials that we can classify. We have on the one hand the conductors, to which of course metals belong, which have a very um, high number of free electric charge per um, volume. And so these charges are highly movable. You have a good conduction, and you can have charge transport. Then semiconductors are somewhere in between, but also kind of a very special case. You can modify their ability to conduct also by doing some doping, and actually also as you cool down a semiconductor, it becomes less the conductivity tends, if you cool it down to very low temperatures, actually, then it is rather vanishing. That's different from a conductor, which becomes increasingly well conducting because you don't have any um, uh, vibrations that kind of hamper the um electrons to move. And then you have the insulator. So this is what we are interested now. These are the dielectric materials. They usually have, so they have almost no free electrons. So in the essence, they are non-conducting. And so how is this effect of this polarizability? How can you imagine that? So there are two kinds of things that could happen. That one thing is that you have atomic charges that are being influenced by an external field, and as a consequence, you have some kind of dipole uh, moment forming. But also, you can have the situation that you have in the material already existing dipoles. And you see that here, this here is some dielectric material. And you have here this composed of these little dipoles. And now if you have an electric field and you bring in this material into this electric field, then this dipole will start to align itself with the electric field, because it has a positive charge on the one side and the negative on the other side. So it will try to align with the field. So you have here this field line, the negative charged side, or the dipole will orient itself so that it is aligning with the field. But in the consequence, you can think of that this section here that has also some electric field by itself. And in the end, you have here something that is counteracting the electric field that is that has been there originally, and in consequence, your now new field is basically superimposed the electric field by the originally given field, and this polarized, that what is contributed through this polarized material, and it will reduce the electric field effectively inside that material. So we have noted down atomic dipoles are generated due to electric field. They can be also already existing, but then if there's no electric field, these dipoles might be randomly oriented. But in the presence of the field, they will, depending on the material, they might be able to reorient themselves such a way that they align, with the electric field, but also that they counteract basically the electric field effectively, and the new electric field that is a superposition of this polarization and the original electric field will be reduced. So the polarization inside a material happens in opposite direction to the external electric field, and this polarized field, this what we denoted here as P, is superimposed to the electric field inside the material. The resulting total electric field is in consequence weaker. And this is actually being taken already into account in Coulomb's law, because Coulomb's law states that the force on a charge depends on the charge and on the charge of the other, basically on the magnitude of the charge and the magnitude of the other charges involved, and on the distance. It's proportional to 1 over the square of the distance. And then we said there's a constant that factors also in. And this constant actually is material dependent. So if you have a different material, your constant changes, and you take account of that by bringing here, instead of just an epsilon naught, that is a constant that is applicable if you are in vacuum, you bring in another factor, which is an epsilon r, which is a relative permittivity. So E sub r denotes the relative dielectric constant or permittivity. So the ER is relative dielectric constant. You can also call it the relative permittivity. That's the same thing. And the epsilon naught, that's the dielectric constant of vacuum, or it is the permittivity of free space. The relative, you remember what the dielectric constant is. This is 8.85 10 to the minus 12. And ER is something that is always larger than 1. So this is just a factor that is adjusting the dielectric constant of free space to that of the material. So this is where we stopped. And the polarization field, which is due to the material property, due to these dipoles here, they contribute then the polarization field. So we name that polarization field P of R, and it is proportional to the electric field. And specifically for us, the example or the scenario we look here, it is basically the proportionality is given by this relative dielectric constant. And for us, this epsilon r here is a scalar value. And this is all we will consider also now here in the lecture, that we have epsilon, this permittivity that or the polarizability of the material enters as a scalar value into the dielectric constant. But I want to give you as an outlook, or to be more complete also, to tell you that there are also other scenarios. For example, you can have materials where the polarizability of the material is spatial dependent, and you might have a different polarizability if you have an E field that runs here vertically or horizontally, and that is a property of the material, that it doesn't have the same polarizability in all directions. In that case, you will have an anisotropic material, but we will not deal with that. We will only consider that we have isotropic material. So this epsilon has no dependence on the spatial orientation of the electric field with respect to the material. Also, what could happen is that polarization is not just linear, it could be also have a nonlinear effect. And also that, however, we will not take into consideration. So the E naught, epsilon naught, sorry, epsilon naught is a dielectric constant. That's how it is called. It is also called, it's called the permittivity of vacuum. Is 8.85 times 10 to the minus 12. That value should also remember, but of course also not forget the unit. It's ampere second per voltmeter. And then the material actually has a permittivity which we denote as epsilon, and that is epsilon naught times epsilon r. So the relative permittivity is basically adjusting the permittivity of vacuum so that you have the proper dielectric, you have the proper permittivity of your material. So that here is basically the absolute permittivity that you have, the epsilon. It's also the dielectric constant, but in this case, not of vacuum, but of the material. Okay, let me start give you the sign up sheet. I also quickly want to mention, next week we'll have the continuous assessment. So this will be on Friday, and it will be in the morning, first thing at 9:30. And you also will receive an email notification. Yes, please. Sorry? No, no, there will be no mock test. So there will be, it will be a closed book. You can use a calculator. It will be heavy on multiple choice tests, questions, but there will be also some non-multiple choice included. So good to also know the most important equations, for example, those that we have given in the wrap up. You also mark those equations like those here. Okay, this is not yet in the wrap up. We have that in the wrap up for the general, for the Coulomb law, but without taking into consideration this relative permittivity. But this is actually, it is quite already implied because we have here in 1 over epsilon, and here we have basically split the epsilon in these two factors, or we have factored out the relative permittivity here. So what are typical values for the epsilon r? So if you are looking at gases or air, then your relative permittivity is usually something like 1.005 to 1.001. So actually, this is roughly 1. So when you are looking at air, you usually also most of the time can work just with the dielectric constant of vacuum because that is so close. Um, very different, for example, it is for water. Water, these water molecules are very highly polarizable. We have a very large number, which is at the order of 81. More common, you might encounter things like what you have in silicon oxide, silicon dioxide. Just to give you some examples. So silicon dioxide, that would have be something like relative permittivity ranging somewhere from 4 to 5. So water, you see, this has a very high permittivity, and that applies for pure water. So pure water is also not conducting, but usually when you have water, then you have some ions in it, and it is also in most cases conducting. But if you really have pure water, the water itself only, then it's not conducting, and its permittivity is then the relative permittivity is around 80. So we are going to use this Coulomb's law, and we see now the force is dependent not only on the charges but also on the type of materials or that are involved. So this is a relation of the force on a charge versus the force that be acting on it if it was in vacuum. You remember the electric field? The electric field is obtained by um, dividing here the force by that charge. So here the electric field. So this here, if you take out the Q here, then this here is basically the electric field which is generated at the position R. So my question for you is, what happens now? Which suppose you have you have you have here one material. Here you have epsilon naught. Here you have epsilon is equal to epsilon naught times epsilon r. You have here your charge. You're looking at your E field point here. Of course, you can say this is, let's say this is your second medium here. This is your first one. And that you can also say the relative permittivity on the first medium here, that would be just 1. If you look at this formula, what is epsilon r that you have to use? You have, I give you this example where you have the one charges in the one medium. You are looking, however, at the electric field in this other medium, in medium 1, and the charge is in medium 2. Are you using the epsilon r of the medium 1 or the medium 2? 1, yeah, because you're looking at the E field in the medium 1. But if you were looking at the E field if you are, this is a function of r, if you're looking at an r which is within medium 2, then you take the epsilon r of the medium 2. So you have, if you the picture what we have just given here as the equation, you have here a multitude of charges distributed in space, point charges in space, which are perfectly localized, and also they are fixed. That is also something which we assume then. Then they generating an E field, and this E field exerts a force on any test charge or any charge that we bring into this field. And this is now described by just this equation above. This is the Coulomb's law. So we have adjusted here, or we have highlighted that this constant in Coulomb's law is a constant which is material dependent. And our next step is now that in the subsequent part of this chapter 1.5, we are going to separate now the material property from the field generating quantities. And by doing so, we are introducing actually another field. This far, we have been always talking about the electric field only. There is a second kind of field which we can define, and this is, you could call it like maybe some sister field, or I mean some close related field. It always goes along with the E field. That is the so-called electric displacement field. So they are going hand in hand, but they are slightly different. And why are we doing this? So that I will show you, because we can get rid of this material dependence for some property that will turn out to be very useful. So we separate material properties from the field generating quantities, and we introduce this D field. You make, it's a D field, and the D stands for displacement, electric displacement field. The electric field is a force field. It basically determines the force which is acting on a charge, because that is how it has been obtained from. It has been obtained from the force by dividing the force field to the charge. So the electric field remains also a force field, but it is now force per charge. So it is a useful quantity as it determines the force acting on charge Q. And the D field, that is actually then connected only to the charges which are generating the field. So I will show you then the impact of that. Okay, what is this electric displacement field? What is our intention? So our intention is now to introduce a relation between the charges and the generated field, which depends only on the generating quantities, but not on the material properties. So we want to get rid of we want to have a field quantity which is only dependent on the charges involved, but not on the material. Our intention is to introduce a relation between charges. These could be point charges. These could be also charge distributions. Charge distributions, for example, like a space charge density. So you see, this far we have been always dealing with point charges. If we look at the force field, we have always used Coulomb's law, that is always based on point charges, but you can imagine that in any practical application, the point charge concept can become very difficult because it's very difficult to assess where your individual charges are really located. Also, you would have to work with this multitude of charges. Practical, you will resort to not take the individual charges, but take a charge distribution. That means you say you have this much charge over a certain volume, and then you would have a charge, a space charge density that would be ampere second per, for example, a cubic centimeter. That would be a space charge densities. In some situations, it's also useful to work with densities not per volume, but per area. You have surface charge densities. Of course, a charge always on the microscopic level, at least you always have a spatial extension of the charge, but you have many situations where the charge actually collect just on the surface of some material or at the surface of some interface. Then you can work with charge densities where you have charges per surface area. So we want to introduce a relation between the charges and the generated field that also Coulomb did, but we don't want to have the material properties in there. We want to have only the generating quantities involved. Generating quantities, that means the charges themselves. And this is the electric displacement that does this for us. The electric displacement field, this is D. Also, of course, I skipped that here now, but it is a function of R. It is 1 over 4 pi, and you get the summation here of I running from 1 to n, and these are the involved charges, the generating quantities, Q sub I, R minus R I, R minus R I, yeah. I think by now now this is slightly different. It's the displacement charge, but you see it really is very closely related to the equation for the set of point charges derived from Coulomb's law. Basically, Coulomb's law using the superposition principle. So this is for the point charges. These are the generating quantities, the point charges Qi. Also, this is important equation. And you see right away the only difference that this displacement field has with respect to the electric field is that the the dielectric constant is present in one and not in the other, meaning you obtain the dielectric you obtain the electric displacement field by multiplying here the electric field with the dielectric constant of the respective material. This is also a very important relation. So let's see what the difference is when we visualize that on the example of a point charge. How is the electric field different now from the displacement field? And assume you have here a point charge. Then we have here our radius, our radius pointing away from the point charge. This point charge Q is generating, it's the source of electric field lines. And let's assume now in a little distance from that point charge, you have some material here, which I depict here in green. This is some dielectric material, and the whole arrangement shall be of radial nature, at least in this direction where we observe. We can say that that material here begins at the radius r1 and it stops at the radius r2. And then let's plot the electric field and what happens to the electric field as it, as we move along R, how does this electric field change? Sketch the absolute value of the electric field versus the radius. We know that in immediate vicinity to the point charge, the electric field is very strong. What happens actually when the radius is 0 for the electric field? If you look at Coulomb's law, if you look at it right at the origin of the point charge and you look at the formula, then you might get to the conclusion that your field becomes infinite because your expression for the radius that enters in the denominator, that becomes 0. But of course, this is not the case. It just means that your model here, you don't really have a singularity at the origin of the charge. Your model for is simply not good here. You cannot, based on Coulomb's law, say the charge at the very origin is infinity. This is just not the appropriate model. Then it would be also become very difficult to, if you have an atom, to really pinpoint what the exact radius is. I mean, where you are, what the exact position for the origin would be. So you have decay of the electric field as you move away from the origin, and it is proportional to 1 over r square. But that is what Coulomb law is giving you if you're in the homogeneous medium, or for that purpose, let's say, if you are in vacuum. Yeah, you're in vacuum. This is this blue line here, because the electric field is 1 over 4 pi epsilon naught. That is a permittivity of vacuum times our charge that we have put there at the origin, and we observe it here at the position RQ. Sorry, we observe it at the position R, of course. The RQ is our origin here. So this is the electric field that we have plotted with this blue line, but we have now introduced, so this is the scenario, pure vacuum. You don't have this material here. Now, I've already plotted it in. There is this material which has here an E epsilon 1, which is larger than 1. So we have a material with epsilon 1 larger than 1. And with material, the electric field looks different. So again, we have the scenario with material, but in the range where R runs from 0 to R1, we are still in the same situation as in the vacuums case. So we have here the electric field being 1 over 4 pi epsilon naught q over r squared, and the orientation vector. In the range where r is larger than R1, that means where the material is present, but smaller than R2, well, our electric field formula is not any much different, but it is a little different. This is obtained from Coulomb's law, so we have to take into consideration the constant that is applicable to the material. So you see the electric field is material dependent, and so is the force. When we have the situation that R is even larger than R2, then we are again outside that range here, where the material is, that we had this material slab we have placed in there. Then the electric field is 1 over 4 pi epsilon naught again. So you see the force field is material dependent, and so is the electric field. And that means this plot here was a plot for the electric field in the absence of the material. And when we have now the material present, then our field here in this range where R is smaller than R1, where we're still in vacuum, remains unaffected. So the presence of the slab of material next to us is not affecting the E field. But then you see, as we enter the material, due to the polarizability of the material and the fact that it has a permittivity which is different from the one of free space and which is larger, always larger than the one of free space, the electric field drops here. But then as we leave this material, it gets back to the value of the that we had for all vacuum. Now, if you look at the situation, okay, I have to shift this down a bit. Yeah, sorry. I will upload it also. Okay, I will rearrange it later. I will shift it down that it's, but I write it on the side now next to it, and I push everything down then and make it a bit more better readable then. So what about the dielectric field? So the dielectric field, you see this is a formulation for the dielectric field. Sorry, not the dielectric field. I mean, for the case where we have dielectric present or not present. So we're looking for the displacement field. We're looking for the displacement field, the electric displacement field. And we want to see in the scenario where the dielectric is present and where the dielectric is not present. So without material, without the dielectric material, what is the displacement field? Without material, the displacement field is 1 over 4 pi q over r squared, and here the unit vector for ER. Yeah, this follows directly here from equation 1.2 to 1. And how is it in the presence of material? What is the displacement field then? The displacement field is then 1 over 4 pi q over r. Any difference? No, there's no difference. And this is exactly the nice thing about it. We have now a field which only depends on the charges, in that sense, in this case Q, that is generating the E field, but they're independent of the material. And if you plot our D field as a function of R, then you have the blue one again in the case where there is no material, but for the case where you have a material in the range from R to R1, it is exactly the same. So what you notice is the D field is continuous. The material, the different material, the material boundary here, that doesn't have no effect on the D field. The E field, however, that shows a kind of jump at the material interface. So let's look at further what the relevance of this displacement field is. That displacement field actually gives us some electric displacement flux, and I want to give you some example what you can understand for that under this. So the intention that we are pursuing is to have a universally valid relation between the charge distribution in space and the electric field and the electric displacement field. And this we achieve by looking at the flux of the vector field. So the flux is basically, well, we can have here an example that is what is penetrating through the surface area. And if you integrate that, then that gives you information, in particular here for our displacement, that gives us information about the sources that are responsible for this flux. So let's look at flux integrals. Those are surface integrals in a vector field, and we use flux integrals where we want to look at the balances of quantities. So we're introducing here mathematical, respectively a physical quantity, which is the flux of the vector field, and we use the flux integral. Flux integrals are surface integrals in a vector field. And by doing so, we obtain some balancing, especially a vector field quantity. So you have here a river flowing, and what is the idea of the flux integral? You have, this is kind of an analogy, we will see how it looks for the electric field and dielectric flux in a moment. But let's assume you have here a vector field. In that particular example, it will describe you the flow of the water, and the quantities, the vectors that you see here, is basically a vector field that gives you the velocity as a function of r of the, well, it could be in the smallest scenario of the water particles. They are flowing each with a certain speed, but also with in a certain direction. So that's what the velocity is. You have the magnitude and the direction. So the quantity of this this vector field would be something in meters per second. And let's sketch here some boundaries here. So basically you have a flow here in this, within these limits here. Then you want to, you could specify here a surface. This is kind of a 3D sketch here. This is my surface. I want to know how much is flowing here of that water through the surface. This surface element that I'm considering has a area which I denote with A. So this is our first scenario. And this surface element is also aligned. We assume here that this flow is now all homogeneous. As you see, they are all pointing in the same direction. The vectors of that vector field, and they are all directed. It's also, okay, sorry, this here should be an arrow here. They are all flowing uniformly in the same direction. And in this case, this surface element is also aligned such that is perpendicular to the direction of that flow of water here. That means if you look at the normal component to the surface element, then this is also perfectly aligned with this with the vectors in the field here. You can have a second scenario, or let's first look at the first one here. So the assumption that we have made now is that we assume that this vector field is constant. We also assume it is constant. That means it doesn't vary with the space, a change of the spatial position, but it's also stationary and also doesn't have a temporary variation. That means no change with time. That means this is not a function of time. It's not a function of time. And in the first scenario, which I've depicted, this surface IA, it is perpendicular to the orientation of the vectors in this vector field. So the surface is a normal vector that we have. The surface normal vector we can give as follows. So this is what we basically will need then to take as a differential surface element when we are doing the surface integration for the flux. You need a vector that is takes into account the size of the surface element, which is given with A, that's the area of that surface element, and the orientation, and that is given with the normal vector. Yeah, so the normal vector, this is what I depicted here in black here, that is a vector normal to that surface element, and the vector A here, the small a with the vector sign, that is combining the orientation of this normal vector and is weighing it with the area of that surface element. Yeah, so this basically includes both orientation and size of the surface considered that is used to assess the flux through that surface. So need a bit more space here. So this n is a normal vector to the surface, but as you know, the normal vector has a property that it is now perpendicular to the surface, but with respect to its magnitude, it's just one, and it doesn't take into consideration the size of the uh, area element. So what is the flux which is flowing through now? So the flux depends on the vector v, that is, and it depends on the element. So this is convenient. We can say that in the scenario 1 here, because we have the assumption that v is constant, so it is not varying over anywhere on this area element. And also the flux, the area element is positioned such that the normal element also is anyway also aligning. So we have the condition that this describes here basically how much water is flowing through this surface element. And in terms of um, flow, you would have here a flux that is given. I mean, the field would be a quantity that is a vectorial quantity, which is given in meters per second. We have an area which is given in meters square, for example, and the resulting quantity would be something meter cubed per second. So this is a volume flux, volume flow, yeah. So if you integrate the velocity over the area, then you get a volume flow. Now, I bring that in. I just want to make some space again here. Sorry. Second scenario is if you orient your surface for which you want to assess the flux through it like this. Again, the area of that element is A. This is now a second scenario. And the normal element is given here. As a consequence, the our surface normal vector that takes both into account the area and the orientation of the area looks like this. So the situation that we have now here is that the surface is actually aligned with the orientation of the vectors in the force field, not the force field, in the flow, in the velocity field here, in the vectorial field. So if you look at the flux of water through the area, then you obtain that just like before in terms of the formula. So this is again obtained from the velocity field, the surface normal vector, and that is, we can write the surface normal vector as a normal vector and the area element. And this is zero just because they are perpendicular, the normal vector and the v. So that is quite obvious. You look at this plot here, you see the water flowing here, not through this area, but it is basically flowing perpendicular to this area. If you compute the flux through the area, then you actually have no contribution in this scenario. And then you can think of the third case. This is when your if you have such a surface element where your normal vector is not aligned with flow. Sorry, that this should be. Of course, it's so this remains unchanged. But now you have an angle between the area of your area element and the vector v. And that angle here, you can also, so this is normal. Maybe I should plot that a bit different. But in terms of you have a normal vector to the area, but between these two you have a vector alpha. So you have an angle alpha. What does it imply for the flux of water? Well, again, you have the same formulation. It is v dot a, but this means it's a magnitude of v times the magnitude of a times the cosine alpha, which is basically the angle between the two vectors here. So to summarize, the flux of a vector field through a surface is calculated by projecting the vector field quantity, in this case v, to the normal vector of the surface. So we have done that for water, and this also will apply for the vector quantity that we have with the displacement field. So flux of a vector field, so we obtain that by projecting the vector field quantity to the normal vector of the surface element. And that you obtain because you have this dot product, right? You see the dot product between the V and the A. Okay. Are you fine with that? Yeah. Okay, good. Then now we can look at the dielectric flux. And here you have the scenario where you have here our charge Q, you have our electric field lines, and you have some kind of volume here. Imagine this to be some kind of tube, but it's closed. And you have here anywhere some surface element. You can divide it into surface elements. And we denote this surface element as A sub j. And also here on the surface element, you have some kind of a normal vector, which is denoted n sub j. And this here, this shall be our some kind of volume. It's a control volume, we can call it. This could be, it doesn't have to be an actual boundary surface of a material as such. It can be just a virtual surface, a control volume. This is just something that you prescribe in there, which is not really physically existent. It is just some control volume where you want to see how much of these field lines are entering into this volume and also how much are leaving this volume. So you have here the red one is the E, the vector field, and the dielectric, sorry, not the dielectric, the displacement field is the dielectric constant times the electric field. So overall, you have here the surface. So this is a control volume, and this control volume has a surface which encloses this volume, and this we denote as dV. This is our closed surface which is enclosing the volume. So the idea when you want to determine now the flux of the displacement field through this enveloping surface, through this delta, sorry, through the enveloping surface, this is basically what we have just put here. This is our enveloping surface. Then how you go about it, you first divide here this enveloping surface into small pieces, small surface segments, which we denote here as A sub j. Each of these elements, it has a certain area and it has an orientation. The orientation is given by the normal vector to this area. And so we can give an vectorial surface element by writing here A sub j, the vector. This here is just the surface, but without orientation. And this is our normal vector, right? So this is what we also just plotted here earlier. So this is our A sub j, and it has this normal vector, and accordingly aligned with that, but weighted is also the vector A sub j. Then for each area element, we calculate the flux of the displacement field through it. That's the second step then. Each area element, calculate the flux d through it. And that means you take d sub j, that is the flux at that area element, times the dot product here A sub j, the surface vector element, and that corresponds then basically, well, you have to make sure that you basically project the d field onto the normal vector, and if they have some angle with each other, the normal vector and the d field, then that is found in this relation alpha, which is the angle. Basically, you have here your d field, you have here a normal vector, and alpha is the angle between the normal vector and the d field, and that gives you the flux element. Now the next step is you sum up the flux contributions through all of the elements A sub j. That means sum it all up from I1 to n, and this is becoming exact as the smaller we make these surface elements. So if we, in the ideal case, do not a summation, but then start to do a surface integration. So it's more exact if we divide our surface in very small areas, A sub j. And then it's, yeah, actually, not accounted enough space here. So, okay, it becomes more exact as we reduce the surface, and actually then if we really make it very small, then if we make it infinitesimal small areas, then we enter into the integration, then it becomes the most, then it becomes even more accurate. Then it becomes ideally perfectly accurate. That means our surface element A sub j becomes a differential surface element, and it becomes a differential vectorial surface element. So then the flux of the displacement field through an enclosing surface, let's make it more clear, the surface of the volume V, and this is this, that becomes then surface integral over an enclosing surface over the displacement field is given like that. This is basically also can write that you see we have on the left hand side the vectorial surface element, and on the right hand side just the surface element, but the vectorial aspect is given here with this normal vector to that surface element. This is important to be comfortable with that here too. So our vectorial surface element is the dA times the normal vector dot the normal vector. And this is the electric displacement flux through an closed surface. So what does 1.22 mean? We sum up basically the D field lines which are penetrating this closed surface of the control volume, and at every point where it is penetrating the surface, we project the D field onto the normal vector of this surface at each point. This is the significance of the equation 1.22 here. You see. So this means we sum up the displacement field. So here the displacement field lines, also we can say, or the displacement fields which are penetrating the closed of the control volume, projecting the D field on the normal vector n of the surface at each point of the surface. Basically, we have with 1.22 the flux of the displacement field through, same thing in short here. And that actually, why that is so interesting, that we will see now when we look at Gauss's law. But do you have a question on this concept here? So we have a surface volume, we have a volume, we have a enclosing surface to this volume, we have segmented this surface into small pieces. Each piece is weighted. Each of these segments basically has a specific area and it has a specific orientation. So we take both the area and the orientation via the normal vector into account. And then we see what are the field lines which are penetrating through this area segment. We project these field lines onto this normal vector to the surface element. I mean, we project the, which contribution is aligned with the normal vector of the surface element. And we are basically summing these contributions then all up. We moving to the infinitesimal areas, and we get this surface integral. So this one here, do you feel comfortable what this here really signifies? That we have here at each point of that surface which is enclosing volume, it's a closed surface, and at each point of the surface we take the component of the displacement field which is aligned with the normal component of that surface element and sum it up by doing this integration. This is our flux through this surface. And there is a very interesting relation And this will bring us to the Gauss law. Sorry, this is, yeah, actually that is double here. That you can just take out. Gesetz means law in German. So it's a central relation, and it's a law of electrostatics. So we have a point charge Q in a spherical control volume, and that we see here, this spherical control volume. You see the sphere here. In the center is our charge Q. This is our volume K, just named K now, like K or C for control, but let's call it K. So then we have this charge, which is located at the origin of the coordinate system, and also the control volume is centered at the origin, and it has a radius. So what you see in red here is, well, actually you see, because the way the sphere is centered, that is on the, or independent. If we use here now spherical coordinates, that would be our unit vector ER, and because the sphere is also centered at the origin, this is at the same time also always the orientation of the normal vector of any surface element. And what is the field of the point charge? The field of the point charge, I'm looking for the displacement field. So field could be, of course, also electric field or any other field, but this, what I want to have now is a displacement field. And we have the formulation for the displacement field of a point charge is 1 over 4 pi q. That is our charge centered in the origin, r minus rq. And we can also write that as 1 over 4 pi r to the power of 3 here. R, because our rq is just in the origin, right? This is 1 over 4 pi, sorry, q over, this is nothing else. And this is just, again, the unit vector ER. And the absolute value of the unit vector, of course, ER is 1. So this is a normalized, the normalization of the vector R here. So everything is here in spherical symmetry. So in particular, the unit vector here is oriented in radial direction. So what is the displacement flux? So we integrate over the closed surface of this volume K. Yeah, so this is our displacement field, and we integrate it, so we get the vectorial surface element here. In addition, so how does this vectorial surface element look like? That is, this one here in contrast is a scalar differential surface element, and this is basically a small part of the area of our enclosing surface of the control volume K. So small part of the area, and that is, in this case, this one here, yeah? So this becomes actually an infinitesimal area, which is contained in this surface dk. So you can also write it like that. You agree? So we are in a very comfortable situation. So the this here basically is dA times ER in our specific scenario, because the control volume is a sphere. It is centered at the origin. So anywhere we have the normal vector to be the radial unit vector. And if you insert that, then you have here the comfortable situation that actually, if you look at this here, at the vectorial quantities, then this here turns to be out 1. So we have here then, let's pull the q over 4 pi out of the integral because it's not dependent on the integration variable. So we have here the integral over the enclosing surface, enclosing the control volume. We are looking at R equal to capital R, right? This is where the control volume is has its border, because we have here a sphere which has a radius capital R. So we want to evaluate our displacement field at the radius capital R. We have pulled out 1 q over 4 pi. So what is remaining here is this term and this one here. Not sure, it's not. Thank you. So what is here in the denominator is actually then r squared. That is not a, we are only interested in the absolute value here. So meaning we can insert now here the fact that r is capital R, and it also is not dependent on the integration parameter. So we can pull that also out, 4 pi over capital R squared. And what remains here is, it's integration over the constant 1 over the surface of that sphere. Okay, this in this particular example is also very simple, but actually we wanted to talk about the integration in the different coordinate systems. I will add that afterwards. So yeah, what is the integration over the surface of a sphere? There's R, capital R. So actually, in this particular case, it's quite simple. I mean, simple because we know the result, because it's just the surface of a sphere, and this is 4 pi r squared. But we will look at it for the more general case, how you really deal with this integration. So this here is just the surface of a sphere. And the surface of the sphere is 4 pi r square. So now, what is the result, the final result? It is wonderful. It is just Q. And what do we find? This is really an important law, that is Gauss' law, is that if you take here the surface integral of a control volume over the electric displacement field, so you're integrating here and over the flux, then the result is the charge which you have enclosed within this control volume. This is equation 1.22. We also mark that. And this is not depending on radius. So you have to stress that here. It is neither depending on radius, and it is also not depending on the size of the volume. It is also not depending on the shape of the value. The only condition is for 1.2. Sorry, I think I have, if I look at it, this was already, sorry, the previous one was already 1.22. This is 1.23. The only condition here, Q has to be inside the volume K. Q element of K. So this is really a very important law. That is the Gauss law. You can have an arbitrary, you can have an arbitrary volume, an arbitrary control volume. This is basically a virtual volume. It doesn't matter. It's a purely virtual volume. You can place it anywhere in your space. And if you integrate the flux that is flowing through the enclosing surface over the entire closed surface, then as a result, you get here the value of all the charge that is included within this volume. And for this particular example, we made this with a spherical control volume because it is easy also to compute that, I mean, to calculate that, because we have this spherical symmetry for this point charge. So we put a sphere around it as a sphere as a control volume. We put the charge also in the center of the sphere. So the alignment of the displacement field is very easy to compute, but it doesn't really matter whether the charge is in the center or anywhere else, as long as it is within this control volume, or it can be also multiple charges, and they can be at various places within that control volume. Then you integrate the displacement field over the entire enclosing surface, and as a result, you get the charge which is included in this control volume. So this is Gauss's law, and I'll give you some examples. But this is also a very important takeaway. So we can do now a generalization to an arbitrary control volume. So we have the case that an arbitrary volume we integrate over the enclosing surface of that volume, only the enclosing surface. We take all contributions of the displacement field which are cutting through this surface of that volume perpendicularly. So we take basically here the vectorial surface element and the dot product with the displacement field. And as a result, you will obtain the charge enclosed in this volume. That means this Q is what you obtain if RQ, that is the position of this charge, is element of the volume. So if it is within that volume. This is, by the way, the equation 1.25. On the other hand, if you take an integration over the surface of that control volume, in the scenario where there's no charge enclosed by or within this control volume, then you obtain 0. That is the case if the charge is either not present at all, or at least if it is not part of this control volume. So you can also say if Q is inside V, if Q is not inside. This is Gauss' law, named after Carl Friedrich Gauss, which you just, on the side notice, you write him like that in German with a different type of S. But you might find it sometimes written like that. So this is other way of writing his name. So example, your Q is here. You have a set of field lines. And you have here your control volume. This is the surface. And this whole thing is a volume. And in this case, what will you get? You will get the 0. This will be this scenario. And in the other case, that would be an agreement with what we just had. You have point charge here. And your control volume is now also capturing the charge. Then this is your result. Oh, let's make that doubles. 2 signs is maybe not so. Let's make this, make that here, like that. Okay. So let's have some more example. Gauss laws for a system of point charges where we have a superposition principle. Or maybe first questions. Any questions? Always welcome. Bring in questions. Or maybe time to let it settle for a while, but please don't hesitate to ask questions. If there's anything not clear, this is very important that this is there are no misconception about that. Oh. So now you also probably can start to appreciate the advantage of having introduced this displacement field, because this integration you have to do over the displacement field, not over the electric field. To apply Gauss law, you do that on the D field, not on the E field. Because you could see that this is not working on the E field. Just if you look at this example, if you were here making your boundary just like that, and you were integrating here over, if you do that over the D field, it is working because the D field is material independent. But if you are integrating over the E field, you have a jump here in the E field because the material is changing, and you will not end up with the value of the charge inside. So if you integrate over the D field, there is no issue if the materials parameter are changing as within your control volume. Let me quickly put here the next formula, but I think then we're already out of time because we have a little bit shorter today for the lecture. So what is the Gauss law for a system of point charges? So basically, we make use of the superposition principle. So we have multiple charges which are denoted Q sub I, and they are located at R sub I. And as usual, we have I running from 1 to n. Then our our charges are located in the volume, in this case now, where R sub I, they are all part of the volume. So Q is the total charge inside the volume. Then we obtain, so we have computed this earlier for a single charge centered at the origin, but if you have multiple charges, and they can be arbitrarily distributed, but if they are all within the volume, then the integration over this displacement field will accordingly give you also the sum of all these charges. And I will show you then some examples, but I think maybe now is a good time to stop. And what time do we meet again today? 2 o'clock, is it right? Yeah? Okay. Then thank you for your attention. And yeah, let's continue in the afternoon.